a number of questions asking me to go over heat capacity in a bit more detail. So I had questions about just the general idea of heat capacity and the formulas associated with it. Then the idea of the different types of heat capacities, so molar heat capacities versus specific heat capacities. And then I had a number of questions asking me about the difference between heat capacity at constant volume versus constant pressure. So I'm just going to review some of those topics. So first, heat capacity, which is given by the letter C. So for however much heat we put in, and heat's given by Q, how much of a temperature change do we observe? So delta T for the temperature change. If we rearrange this formula, we get Q equals C, the heat capacity, times the change in temperature. And this is the basic formula that we saw in class. Now in this case, this C would have a different value for different substances. So for example, oil and water would have different values for their heat capacity. And also, different amounts of the same substance would have different heat capacities. So, for example, 1 gram of water and 10 grams of water would have different values of C. So what is useful for us to do is, instead of reporting just C, is reporting something like the heat capacity per mole of substance, or the heat capacity per mass, for example, grams of the substance. And that's what molar heat capacity and specific heat capacity are. So molar heat capacity is heat capacity per moles, which is N. This would be in units of joules per temperature. So for example, Kelvin per mole, or joules Kelvin minus 1 mole minus 1. So sometimes this would be written as a C with a line over it. Now that's the molar heat capacity. Another example would be the specific heat capacity. This is the heat capacity per mass. This could equally be written with a line over it. The way you'll know the difference is based on the units, and the units for specific heat capacity are joules per Kelvin times some mass unit, for example, grams, or joules Kelvin minus 1, grams minus 1. It's also possible that the temperature for the heat capacity would be given in degrees Celsius, or that the mass might be in kilograms, and you can simply look at the units to know what you're working with, and as long as you make sure your units are consistent, you will be safe. Now let's see, how does this formula have to differ if we're using a molar heat capacity or specific heat capacity instead of a general heat capacity? Well, since molar heat capacity is C over N, we just would need to multiply by N to make our equation equivalent. So Q is equal to N times C over N times delta T. So these N's could just cancel, which would make it look identical to our original formula. So this is just equal to N times C delta T. And now for the specific heat capacity, the exact same thing. So we'd have to have mass, because mass is on the bottom, times C over M delta T, which is just the mass times the specific heat capacity delta T. I'm going to write SP here to differentiate that this is the specific heat capacity and not the molar heat capacity. And for this one, I'll write a little n just to show that these are different. So now the question comes to, how is heat capacity and why is heat capacity different for constant volume versus constant pressure? So at constant volume, let's see what happens. So first we have our general formula, Q equals C delta T. Now let's say that we have a constant volume. Well, at constant volume, I'm just going to write subscripts now to show that we're at constant volume. So the heat at constant volume is equal to the heat capacity at constant volume times delta T. Now we've already shown that heat flow at constant volume is exactly equal to the change in energy. So we know delta E is equal to QV, and this is because at constant volume there's no work. Delta E equals Q plus W, but at constant volume work is 0, so it's just QV. So we can replace over here and say delta E equals CV delta T. Or we can say that CV is equal to delta E over delta T. So the ratio of the change in energy to the change in temperature is the constant volume heat capacity, which is as shown here. Now what about at constant pressure? At constant pressure, we have QP, showing constant pressure, is the heat capacity at constant pressure times the change in temperature. Now we know that QP is equal to delta H because we define delta H, which is the change in enthalpy. We defined it to be the heat flow at constant pressure. So we can substitute that in here. So we have the change in enthalpy is equal to Cp delta T. And so Cp is the ratio of the change of enthalpy over the change in temperature. Now we know that enthalpy and energy are related, but they're not the same. Enthalpy is defined as energy plus PV. So we can see that because CV is delta E over T and Cp is delta H over T, that these values won't be the same. But because liquids and solids don't compress or expand very much, we find that in processes involving liquids or solids, the change in this PV term is very small, and thus the change in enthalpy is approximately equal to the change in energy for liquids and solids. The result is that CV and Cp for liquids and solids are almost equivalent, whereas they can differ for gases which do undergo significant compression and expansion. And that's a summary of heat capacity.